Hello, welcome. Let's try to solve another Leetcode problem. 1063 number of valid subarrays. So for this example, we are getting an integer array nums, and we're going to return the number of non-empty subarrays with the leftmost element of the subarray not larger than other element in the subarray. So this means if we are having a subarray, so for example 2, 5, 3, so the leftmost is 2. So this 2 will be no larger than others. This means this 2 will be less than or equal to all other numbers. So 2 is less than or equal to 5, 2 is less than or equal to 3. So this is a valid subarray. And we are going to return the total number of such subarrays. So the subarray is a contiguous part of our array. Yeah. So the obvious idea is the brute force. Yeah, so this is the brute force. We're going to prepare the length of the nums and the result. So we're going to use the two for loops. So for I in range n and for z in range I plus 1 to n. Yeah, so we're going to prepare an answer equal to 1. So if this nums j less than nums I, this means it didn't meet the condition. It must be more than or equal. Yeah, if it is less than nums I, so we're going to break it. So otherwise, we're going to update the answer. Yeah, so so currently we're going to update the answer. Yeah, so if it didn't meet the condition, so it's gonna break the for loop. Yeah, so this is break is only for the for loop, it breaks the for loop, and then the result gonna plus the answer. Yeah, so according to this way, we're gonna accumulate all the possible results. So basically this is our brute force. It is O(n) square. Normally it would not pass, but it passed for such cases. So normally we should not use this way to solve the problem. Yeah, because this problem is not designed for brute force. Maybe this is a premium problem. That is why it didn't prepare so many testing cases. Yeah. Now we're gonna use another way to solve the problem, because basically this is a O(n) square. This is not what we are required to do. Yeah. Now we're gonna use another way to solve it. So it's going to be monotonic stack. Yeah, so for monotonic stack, normally, this can be all the numbers. We are not sure. Yeah, but for us, the leftmost number going to be less than and equal to all other numbers. So for example, if we have numbers like 1, 2, 3, 4, definitely this is valid. Yeah, because this one is less than all other numbers. So we're going to prepare a monotonic increasing stack. So if some number is lower, for example, this is bigger. So for example, this is 1, this is 4, maybe this is 3. Yeah. So if this number 4 is bigger, so what are we going to do? We're going to pop out this 4. We're going to make it inside of the stack. We're going to make it 1 and 3. We're going to always keep the stack monotonic increasing. Yeah. So this means inside of the stack, so for example, this is the index 0, this is the index 2, and this number 4 is popped out. Yeah. So this means inside of the monotonic stack, we can use the index to check how many possible cases. So for example, for this one, this number 3 is more than 1 because it is monotonic increasing stack. Yeah. So finally, we're going to prepare a dummy dummy number. We're going to prepare a negative one. So if this is a negative 1, this means we will pop out this 3, we will pop out this 1. Yeah. But if we were to pop out this 3, so for example, this index may be 3. Yeah. So we're going to use this index 3 minus this index 2. So we're going to have one case. So it means this number 3. So currently we have the array like 1, 4, 3. Yeah. Now we're going to prepare a dummy place minus 1. And dummy number is going to be a negative 1. This is just used for calculation. Yeah. Now this is our monotonic increasing stack. So this minus 1 with index 3 minus 2, so we have one possible result. Yeah. Now if we were to pop out another one, pop out this one, so 3 minus 0. Yeah. So this means we're gonna plus a 3. Yeah, we have 3 possible results. Yeah, basically this is 1, 1, 4, and 1 4 3. Yeah, and while we are directly pop out 3, this means there's a case of 3. Yeah, so this is the basic meaning of why we can use monotonic stack. Yeah, because if some number in between, this number must be more than this one. It must be a 4. It cannot be 2. If it is a 2, 2 will be here. So it means this number definitely is going to be more than 1. So this means all the numbers from the right side will be more than the leftmost side of this one. Yeah, this is why we can use monotonic increasing stack. Yeah, so this is all the possible cases. But there's also other cases like this number 4. Yeah, currently we didn't yeah, this is this is 3. Yeah, I didn't prepare this number 4, but if this number 4, for example, if it is more than yeah, this number 4 is more than 3, so definitely we want to pop out this number 4. If we want to pop it out, it's going to be index 2 minus 1, it's going to plus another 1. So 1 plus 3 plus 1 is going to be 5. So there are going to be 5 different cases. Yeah, so this is going to be, if we pop out this 4, it's going to be a single 4. So how many cases? Basically we have 1, 1, 4, 1, 4, 3, and 4. 4, 3 is not possible. So another one gonna be 3. Yeah, so those are all the possible cases. Now we're gonna use a monotonic stack. So we're gonna prepare the nums. Gonna be nums plus -1. So this is just a dummy number, just used for calculation. Normally it's gonna be used in monotonic stack, monotonic increasing stack. We're gonna give a smaller number. Yeah, because basically this is increasing, and now we give a smaller number, -1, and we can just pop out all those possible cases, and we're gonna get it, put it to the final result. And let's just prepare a stack. Now we're gonna enumerate all the possible for I in enumerate the nums, and we're gonna check the stack. And yeah, so while stack exists, and on top of the stack, what is the number on top of the stack? So we're gonna take the index. Yeah. First of all, we're gonna find the index. So it's gonna be the stack -1, and this is the index, and we're gonna use the nums, take the index. So if this number on top of the stack, basically if it is more than our current number, yeah, so currently on top of the stack, so for example, if it is a 4 and this number is 2, basically it means it is not possible. It must be a 5, because we want to keep it monotonic increasing. So if it is decreasing, yeah, so if it is more than our current number, we're gonna pop it out. So we're gonna update it to the final result. Let me put a result. It's gonna be starting from 0. Yeah, so result gonna plus equal to we're gonna pop out we're gonna pop out this index. It's gonna be stack.pop. Yeah, and our current index is I, and we're gonna directly use this I minus stack.pop. Stack.pop is another index. Yeah, so for example, let's just use this example, the first example. So currently we're gonna just put 1 inside of the stack, so the index is 0, so this is the index I. Now we're gonna put 4 inside of the stack, so this is the index 1 because 4 is more than 1. Now, because we are having this number 2, yeah, so what are we gonna do? Currently we have this number 2, it is the index 2, we're gonna pop out to this number 4, and we're gonna pop out to this number 4, which is the index 1. Yeah, so we're gonna accumulate the result, and it's gonna be this index 2 minus stack.pop, it is the index 1, so it is 1. Yeah. So after the while loop, we're gonna put it inside of the stack. So stack.append I. So finally, we're gonna return the final result. Yeah, so if it is increasing, we're gonna always append it. But definitely for the final number, it's gonna be a -1, and we're gonna just pop out all the possible cases. Yeah. So for our case, now we have 1, 2, and we have 5, and this is index 3. Now we have index, we have 3. It is the index 4, but we will pop out this 5. Yeah. Now how many cases? It is 1 plus another 1. Yeah, 1 plus 1. Because we pop out this 4, it is 2 minus 1. Because we pop out this 5, it is 4 minus 3. So it is 1 plus 1. So it is 2. Now we have the -1 with index 5. Yeah. So this means for this index 5, it's gonna minus the index 4. We're gonna plus 1. And this 5, we're gonna minus the index 2. We're gonna plus 3. And then we're gonna plus 5. 5 minus this index 0. So it's gonna be a 5. Yeah. Now what's gonna be the final result? 1, 1, 1, 3, 3, 5. So it's gonna be 11. So this is exactly what we're gonna calculate. Yeah. So we have to keep it a monotonic increasing stack. So if some other numbers, maybe it is smaller and this is bigger, basically, yeah, maybe you know this number. So for example, 1, 4, this number is bigger and the next number is smaller. We're gonna pop out the bigger numbers, but this bigger number is gonna always be more than the leftmost number. This is why we're gonna use a monotonic increasing stack. Now let me just run it to have a check. As you can see, it works. Now let me just submit it to check. Yeah, as you can see, it passed for all testing cases, and it's pretty fast. And this is ON time complexity, and the space complexity is also ON because we are using the stack. Thank you for watching. See you next time.